Okay, welcome. Now that we're done with vectors, we can now look at projectiles in Chapter 3. Today we're going to look at the horizontal launch of projectile. First, let's talk about what projectiles are. Projectile motion is any object that is projected into the air, like golf balls, baseballs, bullets, what have you. Anything that's thrown into the air. Things that don't have, propulsion, like rockets, because they have a propulsion, or airplanes, they're not necessarily projectiles. We ignore air resistance. So the saying is, in physics, there is no air, at least at this time, because we want to look purely at the physics and not worry about air resistance and such. The trajectory is defined as the path that the projectile follows. Projectiles are affected by gravity, obviously, because it's near Earth. Therefore, the acceleration of the object is the g value, 9.8 meters per second squared, in a downward direction. And for projectile motion, there are two motions, the horizontal and vertical motion. It's sort of like the relative velocity problems we were doing before, but instead of having constant velocities that are added, we now have one of the motions that's accelerated. So let's look at a horizontal launch. We'll first look at the horizontal motion of a horizontal launch. That is the launch from, say, left to right or right to left. During this time, the speed remains the same. There's no acceleration left and right. The acceleration is downward, so the speed remains the same. No acceleration in mathematical terms, so we say Vx equals 0, and we say Ax equals 0 and Vx equals a constant value. Whatever it had when it was launched, the horizontal velocity remains the same. And so that we say that the initial velocity of x, that's the Vox, is equal to the velocity of x, always. The distance that it travels is called the range. You'll see where that comes up when we do the problems. Now we'll look at the vertical motion. So that's the motion up and down. So we have a left and right motion, left or right motion, and we have a downward motion on a horizontal launch. The speed increases from 0, so it has no initial velocity if it's launched horizontally. That means exactly level with the horizon or the ground. It's accelerated by gravity, so it goes, increases its speed downward. So we say the acceleration in the y direction equals g, and the initial y velocity equals 0. The distance that it travels is called the height, and we generally use a y for that, as with the x on the range. Interesting, the time is the same for both motions, obviously, so it's the time of the projected motion. So we can use a simple, for the horizontal motion, we can use x equals the x velocity times time, and for the vertical motion, we have to use one of these formulas. So either y being the height, initial velocity time. You'll recognize all of these from when we did kinematics. So we're going to use some of those. We mostly use the top equation. I'll give you a hint. Okay, so I have a demonstration to show you. It's a demonstration of two spheres. They're heavy, and one is dropped and one is launched. So watch this. Starring Alan. This is just his mechanism he's setting up. Okay, so he's got this spring trigger mechanism that he can set up this way. He's got one cue ball that's got a hole drilled through it, and when he triggers it, it drops straight down. He has another cue ball, and he launches it. When he triggers it, it launches sideways. So now he's going to put them both on there. So as he triggers it, one ball is going to fall straight down, and one is going to be launched horizontally. And as you can see, both balls hit the ground exactly at the same moment. And then here is Alan cleaning up after himself. Thank you, YouTube. Okay, so as we saw, both objects fall at the same rate, regardless of whether it's launched or dropped straight down. Both objects hit the ground at the same time because they're both under the influence of gravity. And so if we look at a diagram of this, we would have the ball that's dropped, is focusing on this one, is the distance between successive points is increasing because it's increasing its speed. The one that's going sideways, you notice the vector, the downward vector, is the same as the downward vector of the x, and that's increasing at the same rate. But also notice that the Vx is constant throughout. And when we add the two vectors together, we get this resultant, and that's the actual velocity, combined velocity of the two motions. You can see that's increasing both up all the way through. So since the time it takes to drop is equal to the time it is in the air, we can calculate the time to drop to figure out how far it goes. Sorry, that screen didn't show very well, but that's what we're going to be doing. So here's our first example. A tiger leaps horizontally 4.5 meters per second from 7.5 meters. How far does it land? So we set up the scenario. We've got this tiger leaping from the height, so that delta y is going to be the 7.5 meters. It has this initial velocity of 4.5 meters per second, and it's going to project down through that. That should be a perfect parabola, but that's the best I could draw. So what we're going to do is we're going to figure out what the range is, or because it's asking for how far does it land, and it just wants this horizontal distance. We're first going to find the time to drop, just like it was one of those balls, and then we're going to use the time to drop with the horizontal velocity that's given to find the range. So let's go about that. So we are going to go ahead and focus on the vertical motion. Here's our formula that we're going to be using. Delta y equals VOY t plus 1/2 gt squared. Let's replace the values we know. We know that the change in height is 7.5 meters. We know the initial velocity is 0, so that term is zeroed out, and 1/2 negative 9.8 times t squared. So we do a little bit of algebra and multiply 1/2 of 9.8, that's the 4.9, and that's the number we're going to divide both sides by. And then, of course, don't forget to take the square root in this case, so that you can get the time. The negative signs cancel out before the square root. It's convenient. So we get 1.24 seconds for the time it takes for the tiger to drop straight down 7.5 meters. We are then going to use the other kinematics, delta x equals vxt, and then replace what we know. So we know 4.5 meters per second times the 1.24 seconds we just calculated, and that comes out to 5.6 meters. So the tiger will, after jumping off there, will be 5.6 meters from where it leapt from. Pretty straightforward, right? So this is the key, is you figure out the time it takes to drop down and then you use the time because you know that this horizontal velocity doesn't change. Okay, here's another example. A rotten tomato is thrown horizontally from a 56-meter building and lands 45 meters from the base of the building to an unsuspecting physics teacher. How fast was it going when it was thrown? Okay, so we have the scenario of the building and this very large tomato and this unsuspecting physics teacher who loves his students. So what do we know? Well, we know the height of the building, that's 56 meters. We know the horizontal distance, 45 meters, and we know it was launched horizontally with a velocity, and then it follows a trajectory that is parabolic. So what we need to do is we need to figure out this initial velocity, and of course that's in the x direction. So we're going to find the time to drop, and then we're going to use the time and the range this time to find the horizontal velocity. So let's go. So we use that same formula to find the time of drop. Put in what we know. We know it's negative 56. Be sure it's negative if you're using negative 9.8, or else you're going to have trouble with the square root of a negative. Multiply 1/2 of negative 9.8. Move that over. Square root. Don't forget the square root. And so throw that in your calculator, and you'll get 3.4 seconds it takes for that tomato to land down on the teacher. We now are going to use the time that we just did and the range to find the horizontal velocity. So we're going to use that same formula, but this time we're going to put 45 meters in for the range and 3.4 seconds we just calculated for the time. We simply have to do 45 divided by 3.4. The units are setting up for us, and then put that in your calculator, and there you go, 13.2 meters per second. You can figure out how many miles per hour that is if you like, but that's not part of this. I've set an assignment on Google Classroom for you, so if you want to take a look at that, then you can apply these examples to that. Okay, thanks for listening.